Welcome back, dear students. In this video, we are going to look at the third part and the last part of floating point number representation. We already saw how to convert real decimal to floating point binary numbers, to normalize floating point binary numbers, how to convert normalized binary numbers to their equivalent real decimal. Now, in this video, we are going to look at how we can normalize a floating point binary number, provided the number of mantissa and exponent. That is the precision and normalization of floating point binary numbers. In floating point representation, decision has to be made for the total number of bits to be used and the split between those representing the mantissa and those representing exponent. Effect of changing allocation of bits to mantissa and exponent. So we need to know that increasing the number of bits for the mantissa of a floating point number increases its precision and accuracy. So when you are increasing the number of bits the number of bits for the mantissa, it increases the precision and the accuracy of the number. That is, more digits will be available to represent the fractional part of the number, allowing for more exact representation of its value. That's the effect of increasing the mantissa. And you need to know that decreasing the number of bits goes in the reverse order. That is, it will decrease the precision and accuracy. Increasing the number of bits for the exponent of a floating point number increases the range of numbers that can be represented. That is the magnitude of the largest and smallest number that can be stored. So those are the effects of the allocation of bits for the mantissa and the exponent. In order to achieve maximum precision, we must normalize the floating point number. The normalized version of a fractional number provides a unique representation of a number and allows the maximum possible precision with a given number of bits. This is very useful when working with very large or very small numbers. How to normalize floating point number? Very important. One, you need to check the sign of the number from the most significant bit of the mantissa, and we know that if it is 0, it means that it's a positive number, and if it is 1, it is a negative number. The second point is that you need to move the binary point so that the first two digits correspond to the sign. And if it is, meaning that what? A normalized positive number always starts as 0.1 and so on. A normalized negative number starts as 1.0 and so on. Then we need to adjust the exponent so that the value of the number remains the same. Let us look at these examples. Normalize the floating point numbers below, which uses 8 bits for the mantissa and 4 bits for the exponent. And you realize that for the A part, for example, we have 0100.0111. Then we have the exponent to be 1100. So what do we have? That is our mantissa, that's our exponent. We realize that the most significant bit is positive because it is 1. It is 0, sorry. So we must move the decimal point till we get the first 0.1. So for that to be done, I'm going to move 1, 2, and 3. So I'm going to move it 3 times. So this is what we are going to have. Decimal point has moved until we got 0.1 because 0 means that it is positive, and a normalized positive number is of this form. So that's why I moved the decimal place until I got this 0.1. And you realize that I moved the decimal place 3 times to the left, meaning that what? It is positive. Now, you first of all convert the actual exponent you have, and both of them, they're always stored in 2's complement. So always know like that. If not precise, then always assume that the mantissa and the exponent are both stored in 2 complement, because the 2's complement is the notation we use to represent both negative and positive numbers. So now, we already saw when we were working on 2's complement, how to convert a number in 2's complement to the equivalent decimal. And one of the sweetest method is that you consider the most significant digit to be negative. So that's why you have negative into 2 to the power 3. This makes negative 8. This makes 4. So our exponent is negative 4. And now our decimal place moved 3 times to the left. So what happens? The exponent becomes now negative 4 plus 3, which is negative 1. Remember that moving to the left means you are becoming positive. It means that the exponent increases by the number of times, and if you are moving to the right, it decreases by the number of times it moved. So now when we add 3 to negative 4, we get an exponent of negative 1. Now when you convert this, because they said the exponent is 4 bits, when you convert negative 1 into 4 bits 2's complement, you will get 1111. You can do it on your homework and you see the answer will be the same, because when you convert 1 to base 2, you have 0 0 0 1. When you put it in 1's complement, it gives you 1 1 1 0. When you add the 1, it gives you now 1 1 1 1. That is what we have. So the normalized number is 0.10000111, exponent to be 1111. That is a normalized number. For the B part, this is what we have. We clearly see that the mantissa is still positive, so we are going to move the decimal point till we get the first 0.1. And in this case, our decimal point is at this level, so I'm going to move it at this level because this is the first 0.1 we have. So this is what I get, 0.1011. We realize that as we are moving the decimal point and we are ending here, this other bit becomes non-significant, so they can be discarded without any problem. So this is what we are going to have, and we realize the decimal point has been moved 1, 2, 3 times to the right. In this case, our exponent must be decreasing. Now our exponent has this value. When we convert this to base 10, it gives us 5. So moving 3 times to the right, our exponent will be decreasing by 3, making it to be 2. And when you convert 2 in binary 2's complement, it gives you 0 0 1 0. Remember, the 2's complement of a positive number remains the same. You just convert to binary and everything is okay. So our normalized number is 0.1011. As you can see here, these 3 zeros were added just to pad in such a way that we respect the 8 bits for the mantissa. So that is what we have. For the C part, we have 1.111101, and our exponent is has this value. And now, being the most significant bit being 1, it means that the number is negative. So we must move till we get the first 1.0 and so on, because a normalized negative number is of this form. So I have to move 1, 2, 3, 4 times. So this is what we have. And now take note that here we discard all the leading ones except for the one immediately before the binary point, and we pad the mantissa with 0 to the required length, which is 8-bit mantissa. So this is our mantissa. When we move, this is what we get. The other ones are being padded away because remember, this number being negative, if you are to convert it to the equivalent binary, to the equivalent decimal number, as we shall be shifting the decimal point like this, those spaces we have will be completed with 1. That is how it is. Or you can always use the different method we had. We are going to have the equivalent decimal number correct and efficient. So note that when you have a negative number of this nature and you need to move a decimal point till you get the first instance of 1.0, the ones you are having are going to be discarded. So this is what we have. So the decimal place has been moved 4 times to the right. The actual exponent we have, when we convert it, it gives us 1. So we need to decrease our exponent by 4. And taking 1 minus 4, it gives us negative 3. Converting negative 3 into 2's complement, what do we have? Let us do a mental work. 3 in binary, 4-bit binary is 0 1 1 0. No, 0 0 1 1. Yes, that is 3. 0 0 1 1. In 1's complement is going to give 1 1 0 0. When you add 1, it gives you 1 1 0 1. So that is what we have, 1 1 0 1. Now, our mantissa has 1 2 3 4 digits. So we're going to pad it with 4 0, and this is our exponent. So the normalized number is this. That is what we have, dear student. Now, overflow and underflow, important concept you need to know when it comes to floating point representation. Overflow is a situation that occurs when the result of a calculation is too large to be represented with the available number of bits, while underflow is a situation that occurs when the result of the calculation is too small, that is, it is too close to 0 to be represented with the available number of bits. So that is why when in calculations we always provide a number of bits, we must test and see that the range of values we have provide a number of bits enables us to work with the different numbers that are given. That is, for example, if an operation is given to you, provide a number of bits for the mantissa and the exponent, you should be sure that the actual number that were provided to you falls in the range of representation of numbers, and mostly it is the 2's complement. Now, reason for normalizing floating point numbers. The first reason is that what? A normalized number provides more accuracy and precision than corresponding denormalized number. That is the first reason why we normalize floating point numbers. The second reason is that what? Normalizing it provides a unique representation for a number and allows the maximum possible precision for a given number of bits. Yes, because by normalizing floating point numbers, we are given a unique representation of numbers and it provides us with a maximum possible precision with a given number of bits. And the last but not the least is that it simplifies arithmetic operations such as addition, subtraction, and comparison. Because when you're comparing two floating point numbers, the first thing is that we first of all look at their different exponent, and the number with the highest exponent is automatically the largest. And in case the exponent are all the same, that is when we now compare the magnitude of their mantissa. And now, if it comes to addition and subtraction, that you are given two floating point numbers to perform addition and subtraction, always make sure the exponent are the same. Then you simply do the procedure normally and you maintain the exponent. So if you have A having exponent 3 and you have B having exponent 4, make sure B comes down to exponent number 3. Then you perform the addition normally. And you know that if you want to change the exponent, then decimal place has to move a little bit. I hope you enjoyed the video, and at the end, always make sure your final answer is normalized, because denormalizing a number to respect the number of exponent might make the result to be denormalized. So in case your answer after an addition or a subtraction has been done, always make sure your answer is normalized. I hope you enjoyed the video. Do not forget to like, to subscribe, and to share for our community to grow. And see you in the next lesson where we are going to look at another important concept when it comes to binary system. Thank you and see you in the next video.